You teach a child to spot cats by showing them photos and pointing out what is or is not a cat. Their brain quietly locks onto the hidden patterns. That is deep learning, and it is just pattern matching at scale. Deep learning is a branch of machine learning where computers learn from data instead of following rules. The word deep simply describes the layers inside the system. Shallow models stack 1 or 2 layers, while deep models pile up dozens or even hundreds. Each layer transforms raw input into something more abstract. Early layers catch simple edges in an image. Later layers stitch those edges together into recognizable shapes and objects. Picture a factory assembly line where raw data enters. Each station refines the stream before passing it along. The final output is a prediction. At the core are artificial neural networks. These are mathematical systems loosely inspired by biological brains. They process information just like real neurons. A neuron grabs incoming signals and multiplies them by adjustable weights before adding a bias. It feeds that total through an activation function to decide if the signal is strong enough to fire. Neurons group into distinct layers that pass data along. The input layer grabs raw information while hidden layers reshape it before the output layer delivers the result. Stack enough hidden layers together and you get deep learning. Data streams straight from the input layer through every stage during a forward pass. Each neuron applies its weights and activation function to push information down the line. The network checks its output against the correct answer and measures the gap. That mistake gets sent straight back through the system. We call this back propagation. Every single weight gets nudged slightly to shrink that mistake. This step is gradient descent. It is just the mathematical version of trying a little more of this and a little less of that. Run it through thousands of iterations and watch the math tighten. Over time, the weights converge to values that finally produce accurate results. Forget the hard-coded rules about what a cat looks like. The network invents its own internal representation by adjusting billions of numbers until the pattern clicks. The transformer architecture arrived in a 2017 paper called "Attention is All You Need" and became the engine behind every modern AI chatbot. It powers the entire industry. Before transformers arrived, models processed data sequentially like someone reading one word at a time. Transformers changed everything with self-attention and let the model look at every word in a sentence simultaneously. It instantly determines which words are most relevant to each other. You read that sentence about the cat jumping on the table and your brain instantly links jumped back to cat. Self-attention does the exact same trick for AI models. It connects words that sit far apart without missing a beat. Attention processes everything in parallel so transformers can train across thousands of GPUs at once. That raw parallelism is exactly what made large-scale language models actually practical. Every single AI chatbot you interact with runs on a transformer. Fine-tuning takes a model trained on massive general data and adapts it for one specific job. Picture a chef who graduates from culinary school and now runs a trattoria. They skip learning cooking from scratch and focus entirely on your recipes and your customers. That is the entire trick. Start with a model trained on billions of web pages and keep training it on a smaller, specialized dataset. Think medical texts, legal documents, or customer support transcripts. You get serious specialization using just hundreds or thousands of examples and hours of training. That skips the need for millions of examples and weeks of compute. Layer 1 handles feature extraction by reading email text and spotting key signals. The network quickly flags words like winner, urgent free, or click now. Layer 2 takes over for pattern recognition and starts combining those signals. Free, winner, and urgent instantly form a promotional spam pattern, while boss at company com paired with meeting tomorrow reads legitimate. Layer 3 handles the final decision by producing a raw probability score. A result of 0.87 means 87% confidence the email is spam. Cross your threshold and it gets flagged. The model got here by scanning thousands of labeled emails. It kept adjusting its weights until every guess finally matched reality. Deep learning is pattern recognition at scale. Networks learn by tweaking billions of numbers through pure trial and error. Each layer builds a higher level of abstraction. Early layers catch simple features while deeper ones combine complex concepts. Transformers use attention to process everything in parallel. That shift is exactly why modern AI moved from sequential steps to simultaneous understanding. Fine-tuning adapts a general model for specific tasks without starting from scratch. So what is deep learning best described as? Deep learning is a branch of machine learning that uses multi-layered neural networks to spot patterns in raw data. Information flows through deeper layers, and the system builds increasingly abstract representations. Transformer architecture uses self-attention to process entire sequences in parallel. This design is far more scalable than sequential models and now serves as the foundation for modern AI language models. What exactly is fine-tuning and why does it actually matter? You simply adapt a pre-trained model to a specific task using a smaller domain-specific dataset. This approach achieves deep specialization with far fewer resources than training from scratch. If that made it click, subscribe. We break down the frontier of tech and AI every day.